Bougie class today, guys. No need to be sus regarding all this, brother. We're going to jump in. Oh, that felt bad. 4.8 is our focus today. And all of this is just going to be applying trig. Okay, full disclosure. There is a zero possibility that within one section of a course or one day, one lesson, doesn't matter, that you could look at all the applications of trig. It's impossible. Our entire world most of our world can be modeled using this. From heartbeats to the way that our universe is expanding, specifically with the light, and everything comes down to trig at one point or another. As we look through here, we're going to jump right in, and I'm going to talk about a particular thing in our notes in just a moment, but we're going to work on this worksheet right now. That's the goal currently. So that was an awkward little transition. The worksheet, if you're watching this video on the road, the worksheet, there's a PDF of it. Thank you, we pass those back. There's a PDF of it in the class materials on the Google Classroom below where all of our daily stuff is. Okay. In this, we're going to have a lot of examples which we're going to reference here. If you want to put them in your notes, that's totally fine with me, but I don't want you to have to write the problems here today. So, the worksheet that I just gave you is all examples. That is essentially what we jump right into. So right off the bat, our first section is applying right triangle trig. Okay, immediately, we don't have a whole lot more to say. We've looked at SOHCAHTOA, we've seen some identities, we looked at graphing these things. All we're doing is the application part of it. So from here, we're going to jump right into question 1. What I want you guys to do, I'm going to pull up the PDF here in just a minute, but on question 1, I want you to read through it. You do not have to physically work the problem, but with your neighbors, I want to see if you guys can devise a way to work through that problem on the worksheet. Cool. All right, so coming back to it, I'm open to whatever you guys want to suggest as far as where do we start with this. What would you do first, Mickey, just out of curiosity? Identify the parts of the problem. That seems reasonable. Kalisha, what did you do to make sense? Because you did the same thing. You started trying to identify it, but you did something that I love to see. Kalisha drew a picture. Awesome. I think we should. You can do these problems without it, but it's never going to hurt you. So here we go. Are we going to draw like a real house and a ladder and stuff? Absolutely not. Here's a ladder. It's leaned up against a house. Now, there is one assumption in here that you are always allowed to make. If we are working a problem with buildings and things like that, with the unless it's otherwise stated, we assume that the engineers, the architects, built things with right angles, perpendicular to the ground, that is flat at that point. We will do problems where it's not that way, but unless specified, you're allowed to assume it. Which quadrant is my triangle in? It's quadrant 1. Bow ties, butterflies, it says it's here. Everything's positive. So here we go. Of this, where's my 16? Horizontal, vertical, or diagonal? Diagonal. It's 16 long here. Okay, 16 feet. If you guys have never seen this, shorthand for feet is just an apostrophe. You can use FT as well. All right, anything else that I know? Theta. Where on earth would theta be? Bottom left. Remember, angle of elevation. We look up. So here's my theta, and it's 80 degrees. And what am I trying to find? The vertical height. Now, I don't care what we call it. In problems like this, it's natural to call it h. Only reason I'm apprehensive is because h could also be used for what on this triangle? I'm okay with calling it h if you want. More naturally, I would call it y. Only because it's in the y direction. I don't care what you call it. Okay, we're trying to find y. This, hopefully, is not a terrible problem. From that angle that's 80 degrees, Huggins, I'm going to look from that angle as my reference point. Which sides do I have? And I'm looking for opposites, adjacents, and hypotenuse. So I have the hypotenuse, and I'm trying to solve for the what?
The opposite.
So which trig function has opposite and hypotenuse? Sine. So here we go. The sine of, what's the angle we're working from? 80 what? Degrees. equals, what's opposite length? Over 16. And I'm going to solve in one step, and then we'll get an approximation. To solve for y, we are one easy operation away. What do we do? Sean says multiply both sides of the equation by 16. I'm going to switch it up as well. Y is equal to 16 times the sine of 80. Guarantee that this house is less than 16 feet tall. I don't have the number in front of me. What do you guys come up with as an approximation? I'm going to give you a second. I want everybody to type it in. And before, love it. We're going to type it in and see difference. The common mistake here, 15.9, negative 15.9, is because you're in radians. When we are careful and we use degrees, what do we get? Let's go to 4. What was the third number? 6, 9 there? Okay. Feet. Now, in here, and it's going to be important moving forward because I do the same thing here as physics. Anytime we have a contextual problem, you can write like a cave person, but you need to write clearly and explain your answer. How would you word this? I'm going to word this, and there's a million ways to do it, right? As long as you're saying it, don't say it, say the ladder, be specific. The ladder is 0.76, and I will write here, round here, feet up the wall of the house, or up the house. Okay, that's how long we go up. 16-foot ladder at 15.75. Now, is my picture to scale? No, realistically, 80 degrees, this ladder would be crazy, like more realistic laddery. We're like here. Cool. Doable? All right. I want you guys to read through and attempt to work numbers. Let's do 2. We'll do number 2. It's a bit more complex, but rather than me just saying, hey, here's how we do it, I want you guys to see if we can get it. I would advocate work half of it, like here-ish, and then if we need to, we'll work the other half here. Cool. I want you guys to try number 2. A little more complex, not so complex that I don't believe you can do it though. Cool. Talk it out. I'll give us a couple minutes and I will try to give you enough time to work it. If you're watching the video, go ahead and pause it here. Try to work this with whomever you are working with. That came out weird. And we'll meet up in 3, 2, 1. This is a steeple, people. Here's the church. And then I would say the whole thing's a spire. But from the top of the church, the pointy part that sticks out is a steeple. Some of them have bell towers, but I mean, this is a pretty generic looking church. This whole thing. How long is the pole on top of the church is essentially the question. Look, they're putting a steeple on this one. Pretty cool. Sweet. These are the people that this problem was made for. All right. Great question. My bad on that. I had that thought as I was writing it yesterday. All right.
So what's the point of having that angle of 35?
We're going to look at it. So we're going to need it. But first thing, I'm going to judge all your pictures. How many angles are you given? Okay. You do not have to draw a church. Not even a little bit. But if you wanted to, and I don't really want you to, but I want to make sure we're on the same page. Here's a church. Here's a steeple on top of it. Everybody cool with that? Okay, we're standing over here. How far away? 65 feet. And I can look up to the top of the steeple and I see what angle? 35 or 43? To the top of the steeple, what's the angle? So the angles of elevation to the bottom of the steeple and the top of the steeple. So to the bottom is 35 and to the top is 43. Do you guys agree that there's a 43 angle? 43 degree. Right, from all the way up to the top of the steeple. Because 35 and 43 respectively says bottom to top. So the second number goes to the top. A bigger angle, you're looking higher up, aren't you? Okay, from that same point of view, I can look at the base down here, and I get this angle. And I'm going to draw it here. What's that angle? 35. Now, in this picture, how many triangles do you see? Just in the big triangle. Forget the steeple part. I'm going to get rid of the steeple. How many triangles do you guys see there? You see 2? I see 3. I see the little triangle that's at 8 degrees that you were looking at, Huggins. I see the big triangle with 43, the small triangle with 35. Like, there are 3 triangles there. Now, as we're looking at it, we don't know anything else yet. Now, for this, I don't care what we use. For this particular situation, again, don't mix it up with other things, but is there a way to find the whole distance here, the whole y value? And then we need a way to find just this piece, which I'm going to say h sub s for steeple, or s for steeple if you just rather. I don't care how you denote it. Man, how, just from this picture, how would you even get the height of it? So tangent somewhere, forget about the trig stuff. If I ask you just to, how on earth, only looking right here, how do you find this distance? And you don't have numbers yet, but I just want to know there's a subtraction, I think. Y minus h would give me that squiggly line. Or if I'm looking for the height of the steeple, it'd just be y minus the squiggly line, right? If you can find the squiggly line, which is just the height of the church, not the steeple, if you can find the height of the church and the height of everything together, we can get the length of the steeple. From this, I want you guys to keep going for a minute. Raf, are you already done? Okay. I want you guys to use this idea to kick around with it. Try something. You have 2 trig functions you can use, 2 thetas that you can use. It might be the same trig function. I'll give you a moment. Is this problem noticeably a little harder? There's a bit more information presented, but I'm going to tell you something. This is a huge secret to being successful in math, no matter the level that you're at. Try something. As long as you try something, there's a pretty good shot that you're going to stumble upon the right idea. Now, if you have fundamental misunderstandings, that trying something can be hard, but let's just deal with this. As I'm looking, I'm going to elect, for no particular reason, to start with one of the triangles. And just for fun, I'm going to start with this triangle. So I'm looking at just that one right now. Okay, with just that smaller triangle, what's the angle that I'm going to use? 35 degrees, and I know which side of that little triangle. I know the adjacent, and I'm going to use that to find what other side. So let's find the opposite, because we have the adjacent and the angle. Which trig function? Tangent. So I know at this point in time that the tangent of 35 degrees is equal to the opposite, y, over the adjacent 65. Now, I'm just going to jump over here. I don't think this is a big leap. Do you guys agree that y is just 65?
Probably shouldn't use y if y is your whole length of the...
That's a good point. I looked at the y. Thank you, Huggins. I just saw this one.
Yeah.
Thank you for the save. That would have gotten muddled.
Because I did the same thing, and I was going to say, like, y equals, but then I was thinking...
Yep.
That looks wrong.
I agree with you. Height of the church? Thank you. Height of the church is 65 tan 35 degrees. Everybody on board here? I see some erasing over there. What did you erase?
Oh, I just, because I put y.
Same thing that I did. Okay. Now, if I were doing this, I don't know that I probably would have called this y, and y1 and y2 is what I would do if I were looking at it. But it's totally notation choice. Okay. Could we get a number out of that? You could, and we will, but I don't need the actual number. There's our first part. Okay, green triangle. That's done. Easy. Let's look at orange triangle. For the orange triangle, let's dig in. I still have the adjacent. I'm finding the opposite, right? Is it still tangent then? So I'm just going to jump ahead a little bit. Some dots here because it's just the same expression. Y should be equal to 65 times the tangent of what? 43 degrees? Okay. Now, hypothetically, and these aren't the numbers, if this were 10 and this were 4, could you tell me the height of the steeple? It would be 6, right? Because you just did a whole distance minus the height of the church. Could we find the height of the steeple using that exact idea with what we have here? Height of the steeple is equal to y minus the height of the church, which we know is exactly 65. And I'm going to just factor out a 65 because they both have it, right? So this is just so I can write this simpler. 65 comes out, and then we would have on the inside, it looks like tan, what? Tan 43 minus, and I'll put degrees here. You the man, Michael. I appreciate that.
Hey, thank you.
Cool, cool. Diakyu. Minus the tangent of what? 35. Now, do you guys, is it clear why I took the 65 out? Or how I did, rather? Okay, if it's not 65 tan minus 65 tan, I just factored it out. At this point, I wouldn't bother calculating anything out until right now. On your calculator, using parentheses as I have, in degrees, verify we can all get the same thing. I'm going to pause it because this is just a matter of listening. Huggins brings up a good point. I won't plug anything in until I have to. You do not have to do exactly like me. The reason that I wouldn't do this is because I'm comfortable in writing this without making a mistake. I'm still pretty comfortable writing this, although the mistake is getting more likely because I have to put in numbers. What I'm not super comfortable doing, and as these problems get harder and harder, I'm less comfortable trusting myself to do the following correctly.
You lose decimals when you just write it down. That's what you mean.
Well, not only do I lose decimals, but if I round to 4, which is the norm, we're going to get a differently rounded answer. But I'm also concerned about me doing something like this and not even noticing that I've made a mistake.
Yeah.
This is a mistake that I make all the time. Everybody makes mistakes like this. The what do we decide it was called? It's not a typo. A scribal error. I want to avoid them at all costs.
I also like to avoid scribble.
Me too.
But I don't find myself like writing the wrong number.
And good. If you don't, like, if you'd rather do this, that's okay. There are like 30 more pen strokes needed, which isn't a huge deal, right? Okay, as we're here, what does this come out to be? I don't have the answer in front of me. 15.0999. How's that round? 0.1, and it's feet, right? Okay, check it out. The steeple, not it, the steeple is 15.1 feet long. We done. Okay, this next one, we're going to bounce over to notes for just a minute before we work it. Do you guys want a really quick brain break? Okay? Good. That was nice and chill. What are we doing for the brain break?
Your game takes 23 minutes.
Yeah, good luck with that. We'll get a question. We'll do one really quick one. So we're going to go back to our notes for a minute. Thank you guys for sharing that. Looking at stuff. We talked before about bearings. We're going to talk about bearings again a little bit. Okay, bearings. For this, we live on an island, and that island is in the ocean. So pretty commonly we use bearings here, especially for sea navigation. You need to know which direction you're going when you don't have a way to look. So a compass could tell you that.
Is that what a bearing is?
So, not quite. You do get bearings from a compass. Now, for nautical purposes, nautical, the way that these are going to look, which nautical just means water-based. As we're looking at bearings, you have north or south, and I'm going to write it like this. North or south is where we start at. And then some amount of an angle, typically in degrees. And then if you're at north or south, you can only turn one of two ways. You can either turn east, I don't know why these are caps because I don't think they really are, or west.
I think that they are.
I feel like
Direction.
autocorrects.
Direction
We'll check.
I
Okay.
think it is.
So looking at this, when you're on the ocean, it's this way. So for example, we're just going to estimate an angle real quick just to see that we have this. Let's say that I give you this angle right here, and we don't even have to estimate it. Let's say that's 40 degrees. This is an angle in standard position right now. I want us to change that angle of 40 degrees into a bearing. Now, when we're looking at it, you always start with what you're closer to. That angle there, assuming that up is north, down is south, just the regular direction. Are we closer to north or south right now? So we're closer to north. Now, if I were to start at north, like this, to get to the same angle, I start at north and I fall this way. Is that to the east or to the west? That's to the east. And I fall to the east until I get to there. So notice I'm going to leave a little gap here. Here's north where I started. I end at east or go toward the east. And how many degrees did we just have to turn if this is 40? So when we get this bearing, an angle of 40 degrees in standard position becomes this.
How is that 50? Or,
Okay, when we read this, it's always weird because, you know, we read English and we read left to right. This thing is pronounced not starting at north. It's 50 degrees east of north. And we're going to do that Google really quick because I'm mixing between them. Okay. 4 nautical miles is the way it goes. You could say that you are 40 degrees north of east, but that's just wonky. You're not wrong, technically, but nobody says it that way. So we're going to do a quick check here. Is our directions... Just give it to me. Just tell it. North Pole is... North is not. Okay. With that, we're cool with this, I think. Okay, we're not going to do a ton of air problems, but I do want you to be aware. In this one, there's no positive or negative. It's just start somewhere and turn a direction some way. If you're in a plane and you're flying a plane, everything is measured clockwise, which is right away irritating. Clockwise from north. Yep, so you start at north and it's a circle where the first direction you go would be to your right to go clockwise. Is that correct? Yeah. Okay. We don't do that. Other things. If I said, what's the wind speed? And today's a terrible day because it's beautiful outside. Terrible for this example. Nice because it's a nice day. If I said the wind is blowing, like it's gusting really hard, instead of miles per hour, what might I use here specifically? We might use knots. Do you guys know what a knot is?
It's like, isn't it like a, I don't know, I was going to say it's like a water measurement because they use it for boats.
Okay, it gets used for boats and it gets used for planes. Back in the day when you want to know how fast you're going on a boat, if you don't see any land, it's hard to tell because the water moves below you because waves and swells happen, but you don't have a way to track it. So they would tie off big ropes and they would tie knots every specific distance apart, and they would literally count, and as they're going, they'd feed the line out and see how many knots passed over this amount of time. That's where this comes from. What it means for us when we encounter it is nautical miles per hour. I do not know the actual conversion off the top of my head, but a knot is a nautical mile per hour, and KTS is a common symbol that we'll use. All right. With those two things, we have bearings kind of locked in. It's a little bit more. So if we said this wind speed is 60 miles per hour, I'm going to guess that that's like 54 knots, 55, somewhere in there. They're pretty close. All right. Beyond this, we can get more specific, and this is a strange thing to do, but anybody who might be an engineer and wind up doing surveys, which if you've ever seen people down south where they're wearing the vest and they're looking through the camera thing and it looks like they're taking pictures, they're not. They're measuring angles. When we want to go a large distance, would a tenth of an angle make a big difference if I'm trying to sail a ship? Like let's say I'm in England and I'm going to try to sail to the US. A tenth of a degree is only, like it's almost nothing, right? Until you look at the whole globe and then all of a sudden it becomes a big something. you're going to be hundreds, if not thousands of miles off by little deviations in this. When we're looking at it, today we have the ability to say 40.1 degrees, right? That is not the only way we do it. This last little piece, and we'll just say bearings, here they are. We're going to talk about degrees, minutes, and seconds. And we are not going to finish the chapter today, just to break your hearts. Degrees, minutes, and seconds. This is pretty engineering centric, but I want you to be aware that it exists. We're just going to play around with one real quick. A degree, what's 1 degree?
130th of a circle.
So I like the idea, I don't love the number, but 1/360th I think is probably what you meant to
I
say.
don't even know what I said.
1/30th.
30/60th or something.
Yeah, okay. 1/360th of a circle. Everybody agree with that? What's a minute? And I know it doesn't seem the same. 1/60th of an hour. What's a second? 1/60th of a minute. Okay. This country does not like metric measurements, and I don't know why. I do not love this, but it's okay. Let's check this out real quick. I'm going to make a claim in just for a moment. Let's say that we are going to go into real specific angles. So we'll say engineering angles is the name of this small example in our notes. Engineer angle. Now, if I wanted to make something, we'll say theta is, I don't know, we're just going to make up a number, 38.72 degrees. Okay, 38.72 degrees, I can measure it, I can estimate it on a protractor, like we could probably get pretty close. It's quadrant 1, like it's not a nice number, but yeah, you're right, it's the direction it is. Cool. For this angle doesn't look too shocking to you guys, I would imagine. Here's what I want to do though. I want to convert this to degrees. What's the whole degree that we're working with? So how about on this one? If I said round down to the nearest degree, what's a degree? So that's up. Everybody okay with this is 38 degrees? Okay, so we're just rewriting this angle, and we're going to use these minutes and seconds just to make sense of it. So we have 38 degrees, and then we're going to add to this 72 hundredths of a degree, right? Plus 0.72 degrees, 0.72 if you wanted to. Now, do you guys agree that the 0.72 is 72 100ths? That's what the decimal means. Everybody cool with that? Okay, now if I wanted to change this to minutes, I have 72 100ths of a minute right now. How many minutes are there in an hour? So check it out. Here we're going to get the minutes. And then we're going to take one more step here in a minute. I'll change colors. But let's just see what we get. We get 38 degrees. And I'm not going to write the plus. Somebody give me this calculation real quick. 72 hundredths, or 0.72, times 60. $43.2. Okay. Round down to the nearest whole minute. 43 minutes. Now, we still had to do the same thing. And just like before, I'm going to say plus 0.02 because it was 43.2 minutes, right? Or plus 0.2, sorry. Of this time we're not at minutes anymore. We're at what? So take 0.2 of 60 for me again. So what we've just discovered is this 38.72 degrees could be written as 38 degrees, 43 minutes, and how many seconds? 12 seconds. This is a base 60 nightmare to deal with. However, it is used. This is still used today. I am not experienced enough with engineering to give a good justification for why anybody would ever use this rather than just decimals. This is common.
How do you just like go from like you
So 43 minutes, 12 seconds is 0.72 of a full, like, and I know it's odd.
So you can measure degrees in time.
Nope. It's the same word as, that's a great question. If you didn't hear it on the video, Huggins asked, can you measure degrees with time? No. But check it out. I'm trying to think of other places this happens. Trying to think of this. Can you measure temperature with angles? No, but if I said how warm is it in here and you said about 68 degrees, it's the same thing. Same word, different concept.
So minutes and seconds are like the decimal of an angle?
Correct, in this context.
Okay.
Absolutely. It's not time. It's
that's
just
pretty
it's
confusing.
yep, it's just language. But it's just like degrees with angles and degrees with temperature. Same idea, I get it. I think that there's maybe a nice way to do this one more time, and we're going to try it. Because I've never taught this before when we see it, because it doesn't show up in a ton of problems, but anybody who might be an engineer, you'll probably find value in this. Let's make up another one. How about we try, I don't know, what's your favorite degree? Okay. 3 point, what's your favorite decimal? 3, 1. I have an idea. I'm not sure it's going to work. Again, this is the first time I've ever taught this. I've seen it before and it's blah, but again, it might be helpful. What's the biggest degree? So let's convert. We have not theta prime. Theta is in 3 degrees, and then I think I noticed something. I simply took, do me a favor real quick, somebody with a calculator handy, take 0.7 times 60, because I bet it's 43. 42, okay, so this isn't going to work. So let's knock it out then. Plus, and let's check it out, 31 hundredths, or 0.31 of a minute. What do we get there? 18.6. So I know that that becomes 18 minutes plus, and you said 0.6. So let's do the 0.6 times another 60 to get seconds. 36? So that's an interesting question, Sean. It's only based on the notation, right? So like this is a way to measure them, same way that somebody said, how are angles correct? As long as we say this is the way that the rule works, it was called an axiom, a basic fact of the matter. If we just agree at the beginning, you can split in degree into a 60th and call it a minute, and then split that into a 60th and call it a second. These all work. We can do it all. They're just way less common unless you're an engineer. Okay, what I want you guys to do, and this is your homework, quote unquote, number 3 on that worksheet. At the start of class tomorrow, I am going to have you guys write terribly sloppy notation up on the board, because I'm just going to use this. I want you to answer this for me. Okay, full disclosure. There are calculators for these things online. Don't use them. I don't care what the calculator on the internet can do. I care what you can do. Cool. All right. Tomorrow at the start of class, I need to see these. I will give a Starburst lollipop to somebody who does it. I got a bunch of my cards. Zeke loves them. All right. Raiders, good luck today for watching this. Constant shout out. If you have not handed stuff in, please do. Email me, take a picture, email me. I'm going to start putting zeros in on Friday to destroy missing stuff. Cool. Later.